This is the second part, how to construct new functions from a given functions. Here we will speak about composition of functions. So assume we have two functions. F is a function from a set A to a set B, and G is a function from a set B to a set C. We treat functions as relations, and in this relation we have the codomain of F is the same as the domain of G. So we can find the composition of F and G, which is written as G circle F. So by definition, G circle F is all pairs X and Y such that we can find Z in B, where Z is equal to F of X and Y is equal to G of Z. By eliminating the variable X, we find that the set G circle F will be all the pairs X, Y, such that Y is equal to G F of X. Which means that you apply first the rule of the function F on the first coordinate, which is here is X, and then the rule of the second function G on the result of F. Note that G circle F is equal to G F of X. As an example, let F and G be real functions defined by F of X is equal to 2x plus 1 and G of X is equal to x squared. We take F and G with the domain the real numbers and the codomain is the real numbers. We want to find the composition of F and G, which is G circle F, and the composition of G and F, which is F circle G, and determine if these two new relations are functions. Since F and G are functions, we use the rule we give here above. So to find G circle F, by the rule, we take all pairs X and Y such that Y is equal to G F of X. And this will give me all the pairs X, Y such that the second coordinate Y is equal to the square of 2x plus 1. Now G circle F is a relation from R to R, and to find that if it is a function, I have to show that the domain of this function is all the real numbers. So I will take x belongs to the real numbers, and then y, by the formula given here, is 2x plus 1 squared, always will be a real number, and hence the domain of my function G circle F is equal to R. That means G circle F satisfies the first condition of being a function. Moreover, for the second condition, I have to take two pairs, here XA and XB, in the relation G circle F. But then, using the rule of G circle F, we have A is equal to x plus 1 squared, which is the same value of B. This means A is equal to B, and that means my relation G circle F satisfies the second condition of being a function, and so G circle F is a function. Similarly, since G and F are functions and we want to find the composition of G and F, that means we want to find F circle G. Since they are functions, we can use this rule here, but the first is G and then F. So this will give me all pairs X, Y, such that Y is equal to F G of X. So we apply G, the function G to X, and then we apply F to the result. This gives me all pairs X, Y, such that Y is equal to 2x squared plus 1. Now, this definition, F circle G is a function, and to verify that it is a function, we leave it to you. Now we notice that F circle G, it doesn't equal to G circle F. G circle F of x is equal to 2x plus 1 square, where F circle G of x is 2x squared plus 1, and these two functions are not equal. Recall that two functions are equal if they are equal as set. So for example, if x is equal to 0, we have 0 and 1 belongs to G circle F, and also 0 and 1 belongs to G circle F, but it doesn't mean that these two functions are equal, because if we take x is equal to 1, we find 1 and 9 belong to G circle F, but 1 and 9 is not in F circle G. Actually, with 1, we have 3 belongs to F circle G. That means these two functions are not equal. However, these examples shows that always the composition of two functions will be a function. And this is what we will prove in the next slide. So we have the following theorem about composition of functions. So let f be a function from a set A to a set B, and g is a function from a set B to a set C. Then f and g treated as relations, we can find the composition f and g, which is G circle F. This is a relation, will be from A to C. And this relation, the theorem says that it is always a function from the set A to the set C. Moreover, the domain of your new function, G circle F, is equal to the domain of the first function f, which is equal to A. So in the proof, we want to show that G circle F, this relation is a function. That means it has to satisfy for me the two conditions of being a function. And then we need also to prove that the domain of the new composition, G circle F, is equal to the domain of the first one, the function f. Now, as a relation, G circle F is a relation from A, the set A to the set C. So that means the domain of this relation is always a subset of A. Now we want to show that any element in A is also in the domain. I will take A, an element in the set A. Now I will use the fact that A is a function, so we can find a B belongs to B such that A and B belongs to the relation F or the function F. But B now is in the set B, so since G is a function, we can find also C in the codomain of G, such that the pair B and C in the relation G, which is a function. But then, by the definition of F circle G, we have AB in F and BC in G. That means the pair A and C is in G circle F. And this means that A is the domain of my new relation F circle G, and so the domain of G circle F is all of A. Since we take an element X in A, and we found that this element is in the domain. Let's illustrate how this proof works. So the main idea is I will take A is an element in the set A. Then I will know that F is a function from A to B. That means this element will be sent to some B in the set B. And now also I have a function from B to C, which is G. That means this element will be sent, B will send to some element C in the set C. And so I will get my map G circle F will map this A to the element C. And this shows that this A is in the domain of G circle F. Now let's go to the second condition. We take two pairs A, Y, and AZ in G circle F, and we want to prove that Y is equal to Z. Now, by definition of G circle F, that means we have U and V in the middle set B such that AU is in F and UY is in G, because this will give me AY in G circle F. And also AV is in F and VZ is in G, because this will give me AZ in G circle F. Now AU is in F and AV is in F, and we know that F is a function. That means this U have to be equal to V. When we establish that U equal to V, we get that UY is in G and VZ is in G, and of course we have now U is equal to V, but G is a function. That means Y have to be equal to Z. And that means what? That means G circle F satisfies the second condition of being a function. That means it is a function. Let's see the steps of this proof. We take an element A in A, and we assume this element goes to Y and it goes to Z under G circle F. And this is R in the set C. But my definition, that means this element A goes to some element U and then to Y, and it goes to V and then to Z under the function F here and the function G here. But since F is a function, this means U have to be equal to V. Now that means we have the map here. It goes from the same element, say U, to Y and Z, but G also is a function, and that means Y is equal to Z. By this, we finish the second part of these videos about constructing functions from a given one, and we spoke about composition of functions.